Hello, good to see you. There's a lot of people interested in AI and I hope also robots. You saw two of our robots outside there, and I think probably for most of you this wasn't the first time you were seeing them or the first time you were seeing the pictures of these robots, because in general our robots are quite visible. So for those who do not know, then yes, we are doing delivery robots. We're building a network of robots that would essentially create sort of like a plumbing for things, that things would move around automatically. Just like we have plumbing for water, and we have wires for electricity, but we still have couriers coming to us with things and food and things like that. And we want to automate that actually. And the end goal of that is that this is cheaper and this is more convenient for everybody. Just like people, nobody goes to a travel agent anymore to book their flight tickets, but 20 years ago this was really the norm. So I would guess that a lot of you actually know in general what we are doing at Starship, that we are doing delivery robots, that essentially the story that I told right now in a couple of sentences was not really new to you. So please raise your hand if you knew about Starship, what Starship is doing, and knew about our robots. Yeah, so most people know that. But I'm here to present about Starship, so what do? I actually have to present you something new, right? So then actually let's start from some misconceptions that some people actually think that they know about Starship, but turns out that they are actually wrong. So a couple of things around that. So the first thing is that people accept that, okay, yeah, so the delivery robots, for sure, that's realistic, it will happen, in 20 years, when we will have, flying cars, there will be robots that are delivering things. And I'm sure, you're working with these, prototypes of your robots and so forth, but they don't realize, but many people don't realize that our network is actually practical right now. We are doing deliveries in 10 cities right now, every day. And this is before the flying cars, and this is before the self-driving cars as well. Like self-driving cars are not driving without the safety driver yet. Our robots are driving without the safety driver. We used to have people following robots. We still do that sometime in some places, but for a lot of our deliveries, for a lot of our driving, we don't have that safety driver. The robots are going about by themselves. And the same about the drones, for example. Our robots are more practical than flying drones. They will be cheaper than self-driving cars and cheaper than everything else. So these robots are really practical, and we have been doing deliveries in 10 cities for about a year and a half already. So that's one sort of thing that people don't know often about Starship. And let's think about it. What does that mean? That most robot companies in the world are essentially in the prototype stage, but we are already out of that prototype stage. We have more than 100 robots driving around, essentially all the time. So I recently I had a meeting at the Stanford Autonomous Driving Vehicles research group, and I had the meeting with the leader of the group, and just in the middle of the meeting, I had told him all of these things about, we're doing deliveries and blah blah blah. We have more than 100 robots and so forth. But then I just took out my laptop and opened up our internal website and our developer console, and then I started clicking on robots that are live driving around. So here's a robot in Washington D.C. and we got the video feed of the live video of how the robot was driving and what the robot saw and so forth. And this guy was like, "Wow, you can really do that! Wow, these robots are really driving." So I don't understand, what's happening, but for some people, it seems that, they don't still really grasp what does it mean if you have 100 robots driving all the time. So I clicked on a robot in Palo Alto, which was just, a few miles, from Stanford University, and he was like, "Wow, so there's another robot driving, wow, so you can really do that." So it was really impressive for him. So we can actually do the same, to you. You can also see what our robots are seeing and what our internal, developer website looks like. So this is the tools you can access. Like if you're a developer at Starship, this is stuff you see. You see our maps, our operator panel, so you can actually, go and like drive robots, take over control from the autonomous driving system and so forth if you want to, if you have the access level, of course. And then the developer panels, logistics panel, the mapping, and tons of different things. And so let's see how that works. How that works. You can let's click on this operator panel. Then you can actually see the what the robots are seeing. And here's the list of our fleet. There's the Tallinn robots, the Hamburg robots, the Milton Keynes robots in the UK, and the robots in the US and so forth. So you can click on any of these. So let's click on Milton Keynes robot, right? So the video feed takes a few seconds to load, and this is a low resolution video for like privacy reasons. We are not showing you right now the full resolution that the cameras are capturing, but this is a robot driving live in Milton Keynes. You see the map and there's 5 cameras that you can see, and you can switch between the 10 cameras that are in the robot in reality. And you can also pick another robot. So we have also a map. So you see, this is Estonia, this is Tallinn, and you can zoom in and out, and you see where all the robots are driving at any given moment. And let's go to Saue. So we have an operation going in Saue where there are a bunch of robots driving pretty much all the time. And so this is a Saue robot. So it's now approaching a road crossing right now. And you see the green lane that is driving on. This is the sort of the sidewalk lane, and the red is the section of the road crossing that is crossing. Now there's a car coming from the right. So the robot saw the car and stopped, and is now actually waiting for operator confirmation. A human operator steps in and confirms that, okay, even though there was a car, let's cross this road. In general, we have this hybrid control system that the robot is driving autonomously for most of the time, but then human operator help is requested in certain situations in the minority of time. So this is a map of Saue with a bunch of robots driving around, and Tallinn, and there's also other cities as well. So there are different types of data you can access and see things unfolding live. And let's click on Washington D.C. So one robot driving there, and so this is Washington D.C. is a pretty we're driving in the middle of the city, about 1 mile from Donald Trump, and the traffic there is a lot more dense than in Saue, for example. So right now the robot was waiting for a traffic light, and now cars are stopping and driving and so forth, and the robot saw that it's safe and then continued driving, and that's how it works in general. And those lanes on the ground, these are actually mapped by humans. So our robots are not automatically identifying all the time, where they should be driving based on, what they see from cameras or something like that. But they have a human-drawn map of the area and essentially work off that. So that's, in general how things work at Starship, how our robots work, and there's a lot of data in that developer panel, and a lot of that data is recorded and accessible. And the data is super important because especially for this conference, this is machine learning and AI. You can't really do machine learning and AI if you don't have data to train your algorithms on. So let's talk now a little bit of how the software development works in Starship, or what sort of software technologies are we using. And so, my own background, so I'm a software guy. I've been writing code for 35 years now, and I was taught programming, by my mother, and of course, as a teenager, as a teenage boy, so what do all teenage boys, want to write, if they write computer programs, they want to write, computer games. So I started, doing that. And I worked with tons of different types of software, like even music composition and, yes, Skype, and, I've written, hard disk controller, embedded software, and things like that. But my background is not specifically AI or machine learning. And that means that in this talk here, you don't really have this danger that I will present you, tons of, complicated formulas and, things like that which just go, over your head, because I'm not actually an expert in AI or machine learning. But it turns out that's actually not, completely necessary, because there's actually, the critical thing there is that I have written a lot of software. I have had experience with a lot of different types of technologies that rely on noisy data and unstructured environments. Like there are a lot of developers, software developers in the world that who spend their days writing code which is of the style that if this person has access to this account, then show him or her this web page. If not, show an error message, things like that. So I've done that as well, but most of the time I have written code which is not really about whether this person has an access or not, but which has like a very black and white answer, right? But I've written code that doesn't really have black and white answers. It's all probabilistic. It's all based on various types of sensors which are super noisy, and any single measurement could be out from the norm and so forth. So that's actually something that's very much a common theme for all of the robotics development and also I think a lot of the AI and machine learning development, that you can't rely on any single data points, and there's a lot of decisions that are probabilistic. So when people think how are we using AI and machine learning in Starship, then one thing that you potentially could do is that why don't we actually have just this sort of our AI overlord? Let's program a generic AI that just drives the robots, and I guess you could potentially do something like that, but that's not what we're doing at Starship. So in this model, actually, one of the self-driving car companies or hackers in the US called George Hotz or Comma.ai, the company, has actually demonstrated a self-driving car prototype which was built like that. That essentially, what he did was that he just drove his car, recorded what the camera saw around it, and recorded his own control inputs, to the car, and then fed that to a neural network, and let the neural network learn all by itself, that what are the concepts of that there are other cars, and there's this concept of a road, and that when I turn here, then the camera image actually tends to move to the left, and when I turn like that, then the camera image tends to turn to the right, and it's possible, and apparently you can demonstrate a prototype self-driving car doing that, but that's not what we're doing at Starship. And one of the main reasons why we are not doing it that way is that in a practical system, you actually probably need a lot of hard-coded rules. And a lot of them, for example, have to do with hardware failures. So safety is super critical at Starship, and we have tons of different rules and code about dealing with all sorts of hardware failures. Like, so what do we do if one sensor fails, in the middle of road crossing, for example? So you probably want to have hard-coded rules like that. And if there is one downside to big neural networks, then of course one of the biggest downsides is that it's pretty you can't really see what's going inside, and you can't really control or write any sort of these these hard-coded rules. But you can do that actually by creating a lot of different test cases. So I guess we also could create, test cases or training cases for the AI that, okay, in the middle of the road crossing, now the motors are out, or well, let's say one motor is out, but you can still kind of limp or drive ahead. So what should the robot do? But as I said, we are not really doing that. But turns out we don't have to. We are doing actually tons of different types of things based on data and test cases. So the types of things that we are doing. So there's an image of a trash can, and our code, which is deciding how to navigate around obstacles on the sidewalk, for example, it handles differently the stationary obstacles and the moving obstacles. In general, the moving obstacles, you should leave a little bit more room around the moving obstacles. And if something is completely stationary, you can actually drive by pretty closely without reducing the speed too much. So we are actually interested in classifying objects into moving or stationary objects. So how would we do that? Like based on a single camera frame, you actually can't very well do that because this trash can actually has wheels. And it could actually be rolling. And there could actually be a person pushing this trash can, for example, even if you don't see that. So you need multiple sensor measurements, and you need to do some sort of motion tracking. So how do you do like very simple motion tracking? So how did this thing start out when we first implemented this detection of whether this object is stationary or not? So we had essentially two variables. We measured kind of the speed, that based on the stereo vision point cloud, that how fast were the points coming closer to the robot. And the other thing was we actually measured the ordering. We looked at the ordering of the points. Was it always the case that at every frame the points came closer, or did they actually kind of jump back and forth, which would be more like an indicative of some sort of noise. So we had a very simple sort of ad hoc, algorithm. So okay, if the object speed is greater than x, and the ordering is also good or looks like it's moving, then let's call this a moving object, or else it's a stationary object. So that worked, nice. The robot appeared to be making better decisions and so forth. The trouble with that approach is that if you change the code, then how do you know whether that improved it or not? Or suppose you even just by a very simple mistake, you as a developer you created a bug in that code, and it actually might have broken a lot of things in the robot navigation, but you just don't know. So so what do? You create test cases. Test cases that for example, just at the start of it, like 16 different test cases about the positive situations, that there's a moving obstacle, and a lot of test cases also about the negative cases where there is no moving obstacle. And let's now have an automated scoring algorithm that actually takes this is a moving obstacle here, and and then calculate scores for each of these. So how big percent of the time did the algorithm get it right? And if you have an automated scoring like that, and in the end it tells you the final score of 58.8%, it got it right, which is good. Then, well, depending on the scoring, of course, what's the scoring formula. Then you can actually try out different versions of the software. You can actually try different, so the different numbers. Like there was 0.5 times something, or that you can actually try out different numbers and see which work best. So that would be kind of a first step towards a more data-driven approach to these unstructured programming problems. You create test cases and automated scoring. And even if at Starship we don't have this one AI overlord that is driving our robot, then we do have tons of things which have test cases and scoring like that. And by trying different numbers, different formulas, you can actually find out what's the sort of the best best formula that works. So that's in this evolution. This is one step forward from this just an ad hoc formula. This is actually something that's backed with test cases. So if you were already trying out different values of these parameters and different formulas, then you can actually do that automatically, right? So that's the next step in the evolution. You either write or use an already existing software for automatic parameter optimization, where you take your test cases, you take your code, and you have a computer to throughout the night or whatever try out many different parameter combinations and find out which gives the better score. So typically, there's some sort of a numeric gradient descent algorithm to do that, but any sort of algorithm, essentially, that optimization algorithm that does not need to know anything about the formula being optimized, because you want this to be used for detecting the stationary objects and cars and different other things. And the more parameters you optimize, the longer this optimization process takes. And generally, very, very roughly speaking, it's practical maybe up until like 10 parameters or something like that. Because beyond that, just the number of combinations just goes too big. In one of our software components where we have test cases like that, we are typically optimizing about, it has 13 parameters, and we are typically optimizing it on a 32-core machine for about a week. So that's typically how it goes. And of course, you could speed up this using like Amazon Lambda or something like that. Have lots of different machines doing this optimization, but it still takes time. So another step in this evolution going forward is actually to use proper machine learning, to not write this formula by yourself at all, but use like random forests or the SVMs or any sort of properly understood machine learning algorithms and machine learning toolkits to essentially let the machine devise the formula for you. So to do that, you need many more test cases. So all of this evolution, I showed step 0, step 1, step 2, step 3, and so forth. Every step required more test cases. So the first step, maybe I got away with like 16 or 5 test cases or something like that, and I still got some sort of an indication, whether my change in the code improved the score or not. But for proper machine learning, if you want the machine to devise the formula for you, essentially, then you usually need hundreds or thousands of test cases. But they work, of course, really well, and you can draw nice graphs to understand the problem space and what the sort of different numbers mean, and what numbers are useful in deciding whether this object, for example, is stationary or not. Like, for example, whether this ordering stuff is useful or not. So the open source tools tell you essentially all of these things. Now, the next step in the evolution, so you can actually skip all this feature engineering or all of this thinking about what are the different orderings of the stereo point clouds and the calculation of the speed that things are moving towards you and so forth. You can just actually dump the whole stereo vision point cloud, for example, to a deep neural network and let the neural network understand everything about what there is to understand about objects and points, and let it to understand what shape the objects are and so forth. So to do that, you would need even more test cases, but you could actually get really good results. Like generally, you can get superhuman accuracy if you have enough test cases. Then you can get better accuracy than humans in categorizing things, like, for example, whether something is moving or not. And the init here is one example of superhuman ability of the Starship object classification neural network. So this is one of the around 150,000 test cases that we have where the computer or the software component has the task of finding cars in the camera image, and the human annotator missed the car in the middle there, which was partly hidden by a pile of snow, but the neural network still noticed it. So these things happen all the time. Typically these neural networks, the deep learning you can use, or it's best used when you have just so much different features that it's not about just two variables like speed and the ordering or something like that, but you have like the whole like image or like a waveform of an audio recording or something like that. And in order to let you all learn about this thing, if you don't already know it, we have actually created at Robotex this Europe's or perhaps world's biggest robotics challenge in Estonia. We have created a Starship Animal Rescue Challenge. So in about, what is it, like 8 months or something like that, you can try your hand at having robots drive around and identify animals. So this is a test case of there's an animal drawn here, right? And I think this was a reference implementation of this how this challenge would work by our own engineers, and some of them whom are sitting here in this front row. And I think the robot correctly identified this as an animal. So you're all welcome. It's a super, great way to learn and to have fun. Learn about how to code deep neural networks. So you're all welcome there. Now, I talked a lot about needing to have test cases. So how do you get test cases? For our developers, it's kind of easy. Our robots are driving around all the time. We have a fantastic data warehouse set up where you can access all the data that the robots are gathering. So I have a couple of SQL sentences here which essentially ask our data warehouse a question and get back an answer. So how many people here can generally read SQL or generally understand what does this query mean? A lot. Okay, this is really a developer conference. I really can understand that. But I still need to translate for some of the rest. So this query asks our data warehouse, so how many road crossings have Starship robots done since the start of 2017, so a little bit more than a year. And the answer is 1.5 million. And they are all in the database. They all have, attributes like, how many seconds did it take, whether any car is visible, what was the time of day, was it, dark or light, what was the temperature, tons of, other things. And in order to build software systems that, for example, decide whether it's safe right now to drive a crossing or should we wait for like a car to pass and so forth, this is invaluable. That's how our developers create test cases for many software systems. So let's take another query. So we are tracking tons of other things, also not just crossing events. So there's an acceleration event. We have in our database all the events where a robot has sped up or slowed down. We are tracking that because we want the robot's movement to be fluid and not actually braking very hard very often and so forth. So that's important to track for us. We have, for each acceleration event, we have things like time and date, the robot, how many G's was the acceleration, was it like speed going up, speed going down, from what speed to what speed, how long did the acceleration take, and things like that. So the query here asks, so the same question, how many acceleration events have Starship robots had since the beginning of 2017? So what do you think, how much will the answer be? 10? Bigger than 10?
More than crossings.
More than crossings, okay. So more than 1.5 million. So the answer is 712 million. They are all in the database. We all know, the reasons, why it happened, the where it happened. We can do queries, to understand, for example, these, violent breakings. Are they happening more in UK or more in US or more in Estonia? Which version of the robots, which version of the software version, created, more of these violent breakings, for example, or not? So these things are in database. So another query. So how many of these events have happened, during today, from the start of today? And the answer is 1.2 million. So today we have had 1 million. Until this point we have had about 1 million acceleration or braking events. So our developers can get data for test cases by doing queries like that from a data warehouse. And I seriously can recommend you, if you don't like this stuff, then don't join Starship as a developer. You're going to hate it because you're going to be surrounded by 712 million events where your code has behaved poorly and you need to improve it by training a better classifier and so forth. So this is everyday life. And this evolution from step 0, 1, 2 and so forth, all of our developers are going through that evolution with their software components all the time. The example I had, let's actually get a bunch of slides back. The example I had here was something that I created actually over the last weekend to train for a classifier. And over the lunch break today in the office, I discussed with another developer about transitioning his software component from step 2 to step 3, for example. So these things always happen and are everyday life. So, okay, so you get these test cases, but you need to annotate them. To train a neural network or some sort of machine learning system, you need to tell the machine, what are the correct answers for all of these test cases. So you can get, 712 million events where maybe the robot should have done, something differently, but you need to annotate them. That in which cases did the robot do the right job, and then in which cases it did the wrong decision. So that's why we have annotators. So we have 2 people in-house doing annotation full time, and around 15 people in an outsourced team doing annotation. So this is great because we really want our developers to be able to do these SQL queries about acceleration events and tons of other things, and then get, let's say, a list of 5,000 or 10,000 events that they need annotation, and then we want them to be able to turn in their chair and say, "Hi Peter, I'm going to lunch. Could you actually annotate these 2,000 cases for me? Here's the way you should annotate them, and here's the list of the timestamps that you can pull up from our records that you can pull up from the database. These are the things I need to be annotated." And we want Peter to reply, "Yeah, of course I can do that." So that's why we have built in-house annotation tools, and we are generally using these tools. Like for image classification, we can actually annotate something like 2,000 test cases per hour. So if you take an hour-long lunch break, you could actually come back and find that, okay, Peter has actually annotated 2,000 test cases for you. And 2,000 is already enough to do this like step 3 or the proper machine learning type of thing. And here's an example, for example, a screenshot of our car tracking data annotator interface, where the idea there is that these colored boxes are cars, and there are 2 successive frames taken from a camera. So the cars have actually moved during the interval between those 2 frames, and the colors are important because the color tells the machine that this is the same car. So this is training for a car tracking system, not just identification, but tracking that it's the same. It's this car that is moving, from here to here, and we need to do this tracking in order to cross roads safely because we don't want to collide into the cars. So that's it. I think you probably have a few questions for me. I will answer the first question before you ask it. So your first question will probably be, but these things will be stolen. I took one of our robots the first time I took in New York. Then in the airport, in the customs, I opened up the box and showed that okay, we have this robot, and the customs official looked at me and said that, this is New York. This thing is going to be stolen in a minute. And it's not really a minute because, like I said, we have been driving for quite a long time, and none of our robots have been stolen so far. I'm sure you can steal UPS truck if you want to. I'm sure this has been done more than once. I'm sure our robot will also be stolen at some point, but probably not today or probably not tomorrow. But everything in life is probabilistic. As I said, you really don't know whether it will be stolen tomorrow or not. Your questions?
Thank you. Basically, the most popular question from our audience is, what are the weirdest, funniest accident or incident that have happened with Starship?
Yeah, so kids are feeding robots bananas. That's one thing, and the other thing also, if you are a developer at Starship, it's super fun to see. For example, I showed you a robot driving in Saue, and there's a lot of snow, in this winter in Estonia, and our robots are not really built for snow, and we are not offering commercial service right now in Estonia. So if there is a big pile of snow, a robot can actually get stuck, and it's really fun to see, like in the camera image, we know that our own person who is going to come to rescue the robot is about 10 minutes away. But usually, before this 10 minutes happens, there's a mother with a child, on the, what is it in English, the kelk, this red, salvo, kelk, going and say, oh, it's a robot, and they come there and they together they push the robot out of the snow pile, and it drives on, and our robot plays this nice sound, this pre-recorded sound, thank you. So these things are really nice. Actually, politicians really love robots, and they really love to pose with robots, and to take pictures of robot, and then send the picture to their their voter base, and they appear technology friendly and so forth, and in general, regulators are very welcoming towards Starship robots. In general, we do usually in most cases, most jurisdictions, we do need like a special permission to operate, or at least to clarify the legal status with authorities. And Estonia actually became some time ago the first country in the world to change the traffic law to specifically allow robots like this on the sidewalks. And since then, about 5 or 6 US states have done the same to make sure that it's legal to operate delivery robots on the sidewalks of their state. So I wouldn't really say roadblocks. I think the regulators are really welcoming towards Starship robots, and we do play by the rules. So we are not like a certain startup which has a 4-letter name that sometimes goes into cities and starts operating without the permission. So we don't do that.
Christian is asking, how many robots Starship will have in 3 years? Your estimate?
In 3 years, I think I've been part of about 10 startups, and it really doesn't. It's not very accurate to try to estimate the progress of startup in 3 years, because potentially when everything comes together and we have a couple of final pieces of our service that are missing now are together, then we can potentially scale up very, very, very fast. So we are right now at the stage where we have more than one robot, right? So it used to be, like a couple of years ago, it used to be that we had this one robot that developers were taking outside for like a drive, and then they observed, and then they came back and fixed the robot as the first thing because it broke down, and then started analyzing the data. Now it's that a developer comes to work in the morning and makes a SQL query and discovers, okay, we have actually made 1.2 million acceleration events since I was sleeping. So we are beyond the stage where we have just a couple of robots. We have more than 100 in operation right now. Next year it will be more than 1,000. In 2 years, probably more than 10,000. In 3 years, probably more than 100,000. So that's how scaling typically works. Once you have everything together, the market is huge. Like everybody needs this. Just like everybody needs this Lufthansa.com website where they're booking their tickets, for example. They are not going to the travel agent anymore. And the transition was super quick. And here also, our limiting factor in our scaling will be essentially our manufacturing ability. And manufacturing nowadays is pretty quick if you think about how quickly, millions of iPhones were manufactured and so forth. So the Chinese have gotten really, really, really good at it.
Sander's dream is to order food to a suburb of Tallinn. When his dream will come true, using Starship robot?
Let's say in a suburb of Tallinn, I think last October, one year and a half ago in October, I think. It became true at that point. Yeah. But as I said, we are not operating a commercial service during winter right now. But I'm sure we will start towards the summer again.
Are there some other climate limitations?
Not really, because we are also using the Estonian winters and Estonian bad skiing weather as a good testing ground for extreme weather conditions. And we have been driving our robots every day. So we are not offering a commercial service right now throughout the winter in Estonia, but we are driving the robots every day, many, many kilometers every day. And 2 years ago, with our first version of our camera modules for our robots, we discovered that, okay, these camera modules actually did not work in the cold climate. And now we have new cameras, we fixed that. So we have been driving through the last 3 winters in Estonia, and all of the stormy days, all different kinds of weather that has occurred in Estonia for 3 years, and in UK for like 2 years or something like that. So the robots are good at that. There was recently, was it like this week or was it already last week that there was this extreme weather conditions in UK, right, where the public transport was disrupted and the schools were out and things like that for like a couple of centimeters of snow. And then in UK there was actually news stories about our robots, that our snowy robots were still driving in Milton Keynes in UK, and that was a newsworthy event, in the UK.
Thank you.
Thank you.